Hello everyone, thank you so much for joining us today. My name is Victoria Getz and I'm a Senior Marketing Coordinator at 2H Offshore. I want to welcome you all to our webinar today entitled The Importance of Field Measurements for Soil Modeling and Wellhead Fatigue. Before we get started, I would like to cover a few important housekeeping items. Firstly, this webinar is being recorded and will be made available to you soon, so please look out for a link to that in your email. Secondly, if you have technical or content-related questions today, please feel free to ask them at any time. You can use the Q&A box that's located on the right-hand side of your screen. At the end of the presentation, we will go through as many questions as we can, but if you have further questions, feel free to contact our speaker directly after the presentation. And with that, I'm very happy to introduce our speaker today, Bulent Mirjan. Bulent is an engineering specialist at 2H Offshore. He has more than 5 years of industry experience on structural dynamics and monitoring at 2H in Houston. He is also a part-time lecturer in the Department of Civil Engineering at the University of Houston. He received his PhD from the University of Minnesota in 2011, and his expertise broadly covers structural analysis and monitoring of drilling risers, production risers, wellhead, and conductor systems. So now I will turn things over to Bulent to get us started.
Thank you, Victoria, for this warm introduction. I'm very excited to be here today speaking on this topic and hope you will all find this information very useful. 2H has analyzed more than 40 years of drilling riser and wellhead monitoring data from multiple regions, from different water depths, soil types, and environments. So there are extensive learnings from these monitoring projects. So we thought maybe we can share some of these learnings with the industry. That's why today in this webinar we want to talk about the importance of field measurements for soil modeling and wellhead fatigue. Here's our agenda. I'm going to start with a brief introduction to drilling riser systems and fatigue concerns, then briefly talk about soil conductor interaction and modeling techniques. I'm going to give a little bit background on riser and wellhead monitoring systems, just to give you an idea about how the field data is collected. Then discuss soil model verification and wellhead fatigue methodology based on field data. And at the end, I will show the application of these techniques for a drilling campaign example, and then conclusions. Here you see a typical stack-up for a drilling riser system. It is connected to the drill floor of a drill ship or a semi-submersible through a flex joint and a telescopic joint over here. So upper flex joint over here is nothing but a nonlinear spring. And through the water depth, there are slick and buoyancy joints. And at the bottom, it is connected to this lower flex joint and the LMRP and BOP stack. Again, the lower flex joint is a nonlinear spring. And then we have this BOP stands for blowout preventer and LMRP lower marine riser package. The BOP stack sits on the top of the wellhead, conductor, and casing assembly. Riser systems are subject to different vessel motions due to waves and vortex-induced vibrations due to current. Such vibrations are transferred along the length of the riser to the BOP stack and then wellhead and conductor system. Due to cyclic motions, wellhead and conductor system are susceptible to fatigue damages. So, source of fatigue may vary depending on the water depth. In general, shallow water fatigue is driven by wave-induced motions, while deep water fatigue is driven by currents or vortex-induced vibrations. So here I have a couple of videos related to riser and wellhead motions observed in the field. The first video is showing the top of the riser system, tension ring and telescopic joint. It is taken during a high loop current event in the Gulf of Mexico. I think the maximum current speed was close to 4 knots during this campaign. Such current profile or high currents potentially creates a vortex-induced vibration in the riser, and then they are transferred to the BOP stack and wellhead. So in this second video, you will see some cyclic motions on the wellhead at the mudline level. So here you will see that. Um, so yes, this kind of motions. So such motions lead to fatigue damage in the wellhead and conductor system. So I think at this point we should talk about the emerging concerns related to wellhead fatigue. Fatigue was not a major design consideration in the past, but nowadays we are getting low fatigue lives from the analysis. This is mainly due to recent upgrades for vessels, risers, and BOPs, but the design of wellhead conductor system is lagging behind. So this is one of the concerns. Another concern is related to our analytical tools. Are our analysis models really representing the field conditions? How accurate are they? Or our riser or BOP hydrodynamics correct? Or is the soil model defining the soil-conductor interaction correct? So we can come up with a number of questions like this, but these problems can be resolved by evaluating the actual response of the riser and wellhead system in the field. Of course, the physics behind the structural response is very complicated, but at least we can improve our confidence in the analysis results by comparing them with the field data. So, in this webinar, we will demonstrate how to verify the accuracy of soil models using monitoring data and the impact of soil models on wellhead fatigue results calculated based on field measurements. So, first of all, we need to explain why soil modeling is so important. Soil is a non-homogeneous material, and soil-conductor interaction is very complex. For the analysis, soil resistance on the conductor is generally idealized as a system of mutually independent and closely spaced springs, as you can see over here. Soil modeling is important because fatigue hotspot locations changes depending on the soil PY spring stiffnesses used in the analysis. If the spring stiffness is too firm, maybe you can see over here, then the fatigue hotspot, this red dot is representing the fatigue hotspot, it can move above the mudline. Soft soil spring stiffnesses tend to keep the hotspot below the mudline, as you can see over here. So it is very important to use a correct soil model. Soil spring stiffness is affected by a soil type, of course. There are different types of soils, such as clay, sand, or calcareous, and even more. Each of them has unique structural characteristics. For example, if you deal with clay, then shear strength mainly defines the soil resistance. For sand, friction angle mainly defines the soil resistance on the conductor. In the field, of course, it's very rare to see only one type of soil. There are most likely a number of soil layers. So you need to come up with a system of soil PY springs or model representing the field conditions. Common approach to model the soil resistance uses backbone PY curves described in the API recommended practice. It is originally developed for piles. The lateral stiffness at small displacements, you can see in this figure, this is a PY curve, represented by this. So these are very small displacements. So these are very important, especially for fatigue calculations. But originally it's developed for piles, and small displacements are not are traditionally been less of concern. But for wellhead and conductor fatigue, we need to look at these small displacements, and they are basically governing the fatigue response. There are some other types of PY methods implemented due to field variety and increasing criticality of wellhead fatigue. In reality, soil strength degrades due to cyclic loading, as shown in this figure. So strength reduces after each cycle, and the stiffness is also gets smaller. And there is also the effect of structural damping on top of this. But defining a cyclic soil model like this is computationally expensive for regular riser analysis. Therefore, we use equivalent soil springs with monotonic response, maybe as described over here. We come up with an equivalent soil springs to basically model this response. So here also you see different soil models defined for clay. So over here I have API, Janjan, and Zekeri soils. The purple one is showing the API soil, the orange one is for Zekeri, and the green one is for the Janjan. So you can clearly see the difference over here. API is much softer than Zekeri or Janjan for small displacements. Then, of course, the obvious question is, what model should I use in my analysis? I know it is very critical for my fatigue calculations, but which model should I use? So riser and wellhead monitoring can help us with this decision. So here I would like to give you a little bit background on monitoring systems. So why do we need monitoring? We can gain a number of benefits from riser and wellhead monitoring systems. We can do design verification using field data. It helps with operational decision making during severe events, or it will improve or provide some useful information for asset life extension. A monitoring system consists of various components. Motion sensors measure accelerations and angular rates in 3 dimensions. They can be standalone or acoustic. In the standalone system, data is locally stored and then analyzed at the end of the monitoring campaign. Acoustic systems transfer measured data to the topside for further analysis in semi-real time. Strain or curvature sensors can also be used in certain monitoring campaigns. A monitoring system also includes an interface component between the structure and sensor. In some cases, they can be ROV deployable clamps and holders. In some other cases, the sensors can be installed during the riser run. Of course, at the end, recorded data is processed using automated tools, and then the results are visualized using software for operational decision making. It is very important to develop a monitoring system specification at the beginning of a monitoring project. So you need to answer some questions. What's your main goal or measurement interest with the monitoring system? What do you want to capture in the field? You want to identify VIV response or calibrate your riser model, or maybe you want to verify your soil model. Each objective requires different monitoring system specifications. For example, to capture VIV response, you may need a series of motion sensors at the top and bottom of the riser. To verify soil, you may use motion sensors attached to the BOP or around low pressure housing. In other words, a monitoring system should be designed in combination with knowledge of response drivers and also data processing methods. So the question is, how can we verify the soil model using BOP stack motion measurements? Here you see a BOP stack and a motion sensor on top of it. Soil model can be verified by comparing the BOP displacements and inclination, displacement and inclination ratios from field and analysis. Because this BOP response parameter is closely related to soil stiffness. For an assumed soil PY model, the BOP displacement inclination ratio can be determined by free variation analysis. We can determine such BOP response using field measurements as well. Displacements and inclinations are calculated from measured accelerations and angular rates. Then we compare analysis and measured results. If we obtain good correlation between the analysis and the field results, then we can say that, okay, my soil model I use in the analysis represents the field conditions. Well, of course, it's not that simple, because there are some additional concerns. So when using this method, we need to pay attention to some considerations, like I listed over here. Because soil resistance is not only affected by BOP, I mean, soil resistance is not really affecting the BOP displacement angle ratio. It can also be affected by BOP stack flexibility, wellhead stick-up height, soil erosion, or soil scar. So before performing soil model verification, as I described over here, we have to make sure that the analysis model is based on as-built wellheads and soil levels. So if you do that, if you want to evaluate BOP stack flexibility, you can still attach one riser on low pressure housing and another one on top of the BOP. So the difference between these two will be due to BOP flexibility. So okay, so we verified our soil model. Now we can now determine wellhead fatigue using BOP motion measurements and transfer function methodology. So what is transfer function method? So from the analysis, we extract motion time traces at the top of the BOP and stress time traces at the fatigue critical location. So here, this fatigue critical location can be in the conductor. So these green dashed lines are showing what we are getting from the analysis model. We are getting these time traces. Motion time trace over here and stress time trace over here. Then we determine the motion stress relationship. It can be a linear relationship, as you can see over here. We call this as transfer function. Next, we take BOP motion measurements collected in the field. So it is over here. We are getting the measured motions. So this is my BOP motion time traces. And then multiply them by this transfer function to obtain stress time traces at the critical location. Using rainflow counting and ascent curve approach, we calculate fatigue at this location. So we are using this method, we are using this transfer function method to calculate fatigue at the critical location, but in the meantime we are using BOP motions, measured motions. This method gives us more accurate fatigue estimates than a regular riser analysis does, because riser analysis includes a number of variables related to vessel motions, wave and current loadings, riser hydrodynamics, and damping. But we can exclude all of these unknowns from the wellhead fatigue calculations by directly using BOP motions in the field. So in other words, we don't really care what's going on above this BOP, the top of the BOP. Everything is included in this BOP motions. But there's a misconception. Some people think that, oh, we calculate wellhead fatigue using field measurements. It is very accurate. Actually, it's no, because our transfer functions still depend on the accuracy of soil model. If the soil model is not correct, the fatigue estimates can be very wrong. So you have to make sure that the soil model is accurate and or at least verified using field measurements. So now on a drilling campaign example, let's perform this soil model verification using BOP motion measurements and then calculate conductor fatigue, as I just described. So in this drilling campaign example, the water depth is approximately 350 feet. Monitoring system includes two sensors. One is on the top of LMRP, and the other one is on the riser right above the lower flex joint. Accelerations and angular rates are measured in 3 dimensions. Continuous logging is performed at 10 Hz frequency. Conductor soil interaction is defined using nonlinear springs. So for this study, we used two models. One is the design soil model, and the other one is verified soil model. I'm going to go into details of that later. So I don't show here, but the first thing we do in data analysis is to check the quality of data. We check out the sensor noise level, resolutions, voltages, and then calculate motion statistics. The riser and BOP motion statistics are then compared with the measured environment. So here you see two figures. The one on the left shows the correlation of the measured wave height with the riser and LMRP RMS accelerations. Dark blue line is the riser accelerations throughout the monitoring campaign, and the red line is the LMRP accelerations. Due to flex joint between the riser and LMRP, significantly less motions are transferred from the riser to the BOP and then wellhead. The pink line shows the measured wave height. So there is a good correlation between measured wave height and the riser motions. Therefore, we can say that during this monitoring campaign or drilling campaign, riser response is dominated by the wave-induced motions. The same riser and LMRP motions are also compared with the measured current speed, as shown in the figure on the right. The green line shows the maximum current speed. So here I have the details of the soil parameters. They are field specific. I have best estimate and upper bound soil properties over here. It has a very complex soil profile, including sand and clay. It varies from loose sand to stiff clay. So this makes the modeling of the soil resistance very complicated. We need to look into all of these layers, and we need to model them. For this study, we considered two soil models. One is the design soil model, and the other one is soil model verified based on field data. If we use soil model verification technique we described before, which includes BOP displacement and angle ratios, we get the results shown in this figure. Purple dots over here show the BOP response from the analysis based on the design soil model. These dark and blue dots, dark blue and red dots, show the measured BOP motions in two perpendicular planes. As the soil resistance is independent of direction, measured BOP response is similar in two perpendicular directions. So that's why we have in X and Y directions, they look very similar. There's a big difference between the design soil and field measurements. So this, you can see the slope over here. The BOP displacement to angle ratio is 0.24 for design soil model, and it is close to 0.19 for field data. Then we come up with another soil model, which is in good match with this measured field measurements. We can call this calibrated soil model. I know we are not directly calibrating the soil model over here, but I call it calibrated soil model just for the definition. So it's shown by this light blue dots over here. It's coming from the analysis based on calibrated soil model. So here you see what the design and calibrated soil models look like. Calibrated soil model is much stiffer than the design soil model, especially for small displacements. Now we can calculate wellhead fatigue using the methodology we described before, which is based on BOP motion measurements and transfer function methods. So we generate transfer functions for design soil model and calibrated soil model. So we can see the impact of soil model on the wellhead fatigue. In this figure, you see fatigue damage rates calculated based on design and calibrated soil models. Purple line shows the fatigue damage rate, this one over here. It is showing the fatigue damage rate for the design soil model and calculated at the conductor above the mud line. So at this location over here. Light blue line shows the fatigue results at the same location, but this time it is based on calibrated soil model. So it's this one. So design soil model underestimates the conductor fatigue above the mud line. So this line over here, say dark blue, is showing the significant wave height. We can see there is a good correlation with the measured wave height and the fatigue damage rates. As we said at the very beginning, the response is dominated by the wave motions. But the important thing here is the design soil model underestimates conductor fatigue damage above the mud line. This figure shows the remaining fatigue lives at the end of the drilling campaign for 4 different locations. We consider 2 locations above the mud line in the 36-inch conductor and 20-inch casing, and 2 other critical locations below the mud line. Again, the results are based on the design soil model and calibrated soil model, the purple one and light blue one over here for 4 different locations. We can say that design soil model overestimates fatigue life of the conductor above the mud line by a factor of 20 almost. So in conclusion, soil modeling has a significant influence on the wellhead fatigue calculated based on monitoring data and transfer function methods. Soil models can be verified using BOP motion measurements in the field. One motion sensor is sufficient to capture BOP motions and assess wellhead fatigue. But monitoring system including wellhead and BOP sensors can be used to determine BOP flexibility. Conductor fatigue life can be overestimated by a factor of 20 if the soil model is not verified with field data. Of course, this is just an example. This is just for an example monitoring campaign, but of course more field data is required to verify to this difference. With that, this is the end of my presentation. So if you have any questions, please send them.
Thanks, Bulent. That was great. We do already have a few questions that have come in from our audience, so I'll go ahead and get started asking those. The first question is, for wellhead fatigue monitoring data, could you please clarify how many motion sensors and stress strain gauges you use, as well as their placements?
So for this example campaign, we have only two motion sensors. One is at the top of LMRP, and the other one is right above the LFJ, lower flex joint. To calculate wellhead fatigue, we just need actually one sensor at the top of BOP, and we can, using just one motion sensor, we can evaluate the soil model and then also calculate fatigue at the critical location using transfer function methodology. But of course, you can also provide, attach strain sensors. They will also provide additional information, and they will be, in some cases, maybe they might be, of course, more accurate. But it's not very easy to install strain gauges on the conductor system all the time, and the reliability is a little bit less comparing to motion sensors, because if you are interested in the fatigue below the mud line, you need to put them and they may be damaged, so reliability is a little bit less for strain gauges, especially if they are below the mud line.
Okay, great. Our next question says, I have a question on how the BOP response is calibrated to soil models. Is it analytical, or have you used FEA?
Yeah, it's a very good question. Yes, when soil model is also, okay, when we do soil model verification, BOP hydrodynamics are also important. For this study, we perform analytical study to evaluate the effect of the BOP hydrodynamics. They are minimal, especially for this monitoring campaign. So yes, we just perform analytical study for that.
Okay, another question is, how can you simulate fatigue in wellhead systems without having the detailed drawings or the information of wellhead components? Sometimes these are normally kept by the manufacturer.
Yes, so it is just going to be an approximation. So what we do in, it's not a 3D modeling of the wellhead and conductor system. If you want to do more detailed analysis, you can generate 3D models. But what we do over here is typically in the industry, we model using we model this conductor and casing system using pipe-in-pipe modeling, and so they will be line elements in the model. But of course, if you want to do 3D modeling, it will be also, can be also done.
Okay, the next question is there a benefit to suppressing the fatigue hotspot, as the fatigue performance of the casing is more predictable than that of the wellhead?
Could you please repeat the question?
Yeah. Is there a benefit to suppressing the fatigue hotspot, as the fatigue performance of the casing is more predictable than that of the wellhead?
Yes, you can predict the, yes, wellhead is more complicated, so we can calculate the fatigue in the casings and conductor, because the geometry of the wellhead is more complicated than the casings and pipes. Yes, it can be done.
What about this one? Does the downward force generated by the BOP/riser stack weight have any significant effect on the wellhead fatigue or the failure?
So the compression coming from the BOP, at some point we did an analysis on this using field data again. We looked at the effect of the tension variation in the in the in the fatigue calculations, especially coming from the axial force due to the weight of the BOP. So this variation has no influence on the yes, it has some influence, but it is minimal comparing to fatigue due to bending of the conductor system.
Okay, next question. How do you measure fatigue damage?
Yes, we are not directly measuring fatigue damage over here. We calculate the stress time traces at the fatigue critical location using BOP motion measurements, and then use transfer functions. And then we use rainflow method and assign curve approach. So we don't have any tool at this point to obtain the wellhead fatigue directly.
Next question. How do you know that it's the soil model that needs to be calibrated and not something else?
Yes, so this is actually related to the previous question, very similar, the effect of BOP hydrodynamics. Yes, there are some other analysis parameters affecting the BOP displacement angle ratio, such as I listed some of them in my presentation, such as BOP stiffness, stick-up height, soil erosion. BOP hydrodynamics is one of them, conductor casing stiffness. Some of these parameters can be excluded if as-built system is modeled. And some of these parameters may not be that effective. They may not affect the results as much as soil stiffness. So, yes.
How accurate are the measurements?
I didn't go into the details of data QA, but first step in data analysis is to check the quality of measured data. You need to check out the sensor noise level, resolutions, compare them with the sensor specification, and then you will be more comfortable with the measurements, and you know that your measurements are the sensor spec.
Another question we had, what is the best soil model in your opinion?
Well, this one is a little bit tricky. Yeah, it's difficult to say one soil model is always better than the others. A number of soil model verification study using field data need to be performed before making any proposal for the best soil model.
Okay, I think we have time for a couple more. This question says, in the case study, was the conductor jetted or was it drilled and cemented? And if it was cemented, how do you model that?
In this case study, it was jetted. So when we model the PY springs, we are using the conductor OD to calculate the PY spring stiffnesses. But if you have a cemented case, then you will use the hole size when defining the spring stiffnesses.
Another question, where is the best place to put the monitoring device and why?
So as I said in my presentation, it depends on your objective. If you want to verify the soil model using monitoring data, then one sensor on the top of the BOP and another one on the maybe low pressure housing will be sufficient. So the difference between them will give you an idea about the BOP flexibility. And also, we want to use motion sensors at the top of the LMRP when we do the soil model verification, because most of the time motions are very small, close around the low pressure housing or wellhead. So we want to obtain good, say, signal to noise ratio. That's why we tend to use data from the LMRP sensor.
Okay, we also had a question that says, I'm a geotechnical expert and I didn't see any mention of soil damping. Can you comment on that, please?
Yes, I tried to explain it a little bit, but didn't go into too much details. Dynamic soil response includes various effects, such as strength degradation, stiffness degradation, soil damping. All of these effects are approximately taken into account in the analysis by modeling equivalent PY spring stiffness response under monotonic loading. So you can model, as I showed, a cyclic response, but it is very computationally expensive. So in regular riser analysis and fatigue calculations, as a first step, we do we use monotonic response.
Another question we got said, how do you consider the vessel motion in the fatigue calculation?
So in this study that I showed, or in this presentation, we are not using vessel motions to calculate wellhead fatigue. We use measured BOP motions for wellhead fatigue calculations. So we don't need to know vessel motions or wave motions or riser response. All of these effects are transferred into BOP motions anyways. So we are directly using BOP motions, and we know that these BOP motions will lead to fatigue accumulations in the wellhead and conductor system. I hope I answered your questions, but let's see.
I think we have time for one more. This one says, you have multiple soil layers in your model. When you calibrate your soil model, how do you manage this condition, and what's the best recommended practice?
So when we model this soil springs, we have the closely spaced springs. So for each layer, we use recommended or industry standard soil PY spring models. We use them for each layer. They will be different, but this is the way we do it. They are closely spaced, maybe 1 meter or 0.5 meter spacing. So for each layer, we will have enough number of springs, so we will be able to model them.
Okay, well, thank you, Bulent, so much. I think that's all the time we have for today. As we mentioned earlier, if we didn't get to your questions, I know there's a couple we weren't able to get to, or if you'd like to continue this discussion, please reach out and contact Bulent directly using the details provided here on the screen. And thank you to our audience for your time and participation. We hope you all found this useful and will join us for more webinars next year covering a range of riser and subsea topics. Again, please look out for the recording of the webinar in your email in the next 24 hours, and we hope you all enjoy the rest of your day. Thank you.
Thank you very much.